All right, let's take a look at problem 11.12 and see which reactions are spontaneous at 25 degrees and also the temperature ranges at which point the reactions will become spontaneous. One thing to note here, I got this from a textbook that had the values in kilocalories per mole. Let's just replace them with kilojoules per mole and joules per mole Kelvin to make our lives easier. And I also did that in your book. All right, the first thing that we want to do is actually look at the data before we begin to see if temperature will play a role in either reactions A, B, or C. And the first thing to note is that it shouldn't play a role in reaction A. Remember, temperature will only be the deciding factor when the signs of delta H and delta S are the same. They aren't in reaction A, and that's our indicator that we need to think a little more carefully about whether or not the reaction is always spontaneous or never spontaneous. And in this case, since delta H is positive and delta S is negative, it's non-spontaneous at all temperatures. And you can figure that out from the definition of delta G being equal to delta H minus T delta S. For reactions B and C, the signs are the same, so that's our indicator that we should calculate the temperature at which point the reaction will be at equilibrium. So let's do it for B first. This is given by delta H over delta S. You can always derive this by setting delta G equal to 0. This calculation, after we convert delta S to kilojoules or delta H to joules, gives us an equilibrium temperature of 7,448 Kelvin or 7,175 degrees Celsius. Remember that the answer is always spit out initially in Kelvin, not in Celsius, and you have to backtrack and convert to Celsius. So we have to think about whether or not the reaction is spontaneous above or below this point or this temperature. So let's think about delta G and the equation for delta G here, and which one of these terms favors spontaneity. Well, a positive value for delta H certainly doesn't, because it tends to make delta G positive. So we want to increase the magnitude of T delta S, and we can do that by increasing the temperature. Now, unfortunately, that means that this reaction is spontaneous at all temperatures greater than 7,200 degrees Celsius, and I rounded to two significant figures, which basically means for all intents and purposes that this reaction won't happen because the temperature has to be so high. Let's take a look at C. Again, we're going to take the same approach because temperature does matter here. The signs are the same. And we get 464 Kelvin and 171 degrees Celsius as the equilibrium temperature. On the contrary to reaction B, C has a negative value. It's an exothermic reaction, which is good for spontaneity. It tends to make delta G. So we want to decrease the magnitude of T delta S relative to delta H by lowering the temperature. So the reaction should be spontaneous at all temperatures lower than 191 degrees Celsius, much more reasonable than in reaction B. Again, remember, the only time you're going to apply this equation is when the signs of delta H and delta S are the same. If you apply it to a case like A, you're going to get a negative temperature, which can't happen because Kelvin can never be negative. Good luck.